How's that? Everyone seeing this? Oh, that's really annoying. I thought you were using the same boring old 3x4 screens as Auckland, but you've got nice letterbox screens. I'm sorry, this is going to be narrow. Hey, you all set to go? Yeah, cool. Huge thanks to the Wellington people I've been promising for years to give this talk. So here at finally out. And I'm excited to be here. It's always a real pleasure to give a talk. In this case, I guess to a mixture of Victoria people and Wellington Astronomical Society people. But one of the great things about astronomy is the huge community of passionate people who are kind of gathered around the field who aren't depending on it for a paycheck. And so, yeah, particular pleasure to be here today. So what I want to talk about in some ways is about the sort of more professional side of astronomy, in the sense that I want to talk about the ways in which New Zealand can engage with big science. And so big science, for those of you who haven't heard the term before, possibly to those of us of a certain age, other than a Laurie Anderson album, is a term that grew up in the United States, I think, after in the wake of the Second World War, and it refers to science that is based on facilities that are used by many people and not just by individual labs. And so, if you're in many places, you can go into a lab in a biology building and there'll be a sequence of labs that are managed by a sequence of investigators and have pretty similar kit and activities. The details of the activities will be different, but the tools they're using will be the same. In the case of things like astronomy and particle physics, the kit that we use to do our work is typically expensive. And so you have many people who have to come together to agree on a particular set of resources and tools they want to do their job. And that big science, big cost, big teams, relatively small numbers of pieces of equipment is characteristic of astronomy and astrophysics. But it's also true that this field also has big ambitions and big impact. So roughly half of the physics Nobel Prizes in the last couple of decades have related to research that's done as part of these large collaboration with big pieces of equipment. And these things, as much as Tycho Brahe apparently spent a small Danish kingdom into the ground in order to build his equipment in the 1580s and 90s, these are things that we spend money and effort and treasure on in order to make sense of, to discover new deep things about the world. And so what I want to talk about today is how it is that we can do this from New Zealand, why it is to some extent that we should do this from New Zealand, and how it is that we're actually making it work from the perspective of New Zealand. And so I'm going to go a little quickly, I guess, over some of the details. One of the nice things about talking to an audience of astronomers or people with a background in astronomy is that I don't have to tell you that this is the Milky Way galaxy. It's also taken from Wellington, but I think this particular one might be on Wikipedia. It's just a beautiful image, and I guess part of astronomy has this this connection to the first people who looked up at the sky and tried to figure out what it was that they were seeing and how it works. And so we can fast forward. This is an image that, other than that it's a photograph, this is something that the first human beings would have been able to see. And we fast forward to this, which the aficionados will know is, how do we know this is the James Webb Space Telescope?
Fraction spikes.
It's the spikes, it's 6 spikes, right? That hexagonal mirror gives you 6 spikes in your diffraction spikes rather than 4 that you get from the Hubble telescope. So whenever you see the 6 spikes, you're looking at the J. And this is like every one of the spots in this image is a galaxy that could be as big as the Milky Way, the object that we saw there. And in particular, this one, the distant or more deeper red galaxies have been twisted gravitationally by this big object that sits in the middle of this image. It's an astonishing thing. And the pointy objects, the things that are actually seen as points by the JWST, those are stars inside of our own galaxy. So most of the objects in this image are actual galaxies. with billions of stars. I hope I'm getting this right, Yvette. I'm just, if not, I'm going to be hearing about it in quite some time. I'm just crossing my fingers here, because more of a theorist, right? So what I want to do is okay, so we sort of take it for granted, we're among friends, that this is something that we can do and something that we can make sense of, that it tells us things about the universe that we live in. And so what I want to do in this talk is to talk about two different experiments, two different collaborations that New Zealand is involved with. The first one of those will be the Vera Rubin Observatory, and the second one of those will be the LISA gravitational wave experiment that's been built by the European Space Agency. And so Vera Rubin, for those of you who are not aware, she is one of a number of people who played a key role in figuring out that it seems that most of the stuff that we see in those galaxies, or when we look at a galaxy, actually most of the material of the galaxy is stuff that not only doesn't emit light or doesn't absorb light, but is not made of atoms. It's not made of anything that lives in the periodic table. It's not made of anything that's inside of the standard model. As it's, the kind of particle physics equivalent of the periodic table as it's been teased out at LHC and at the Tevatron in Chicago and in other institutions. Rubin in particular, she played a key role in figuring out that spiral galaxies, that the outer parts of the spiral galaxy moving at about the same speed as the inner parts. And so a very different picture from what we see with the planets, where the outer planets not only have to go in a longer loop around the sun, but also move more slowly because they're primarily being pulled by the gravitational field of the sun, the one massive object in the solar system. But in the case of galaxies, it seems that despite the fact that most of the light comes from the center of the galaxy, most of the mass in the galaxy seems to be distributed more evenly, so that light does not trace mass. And so as a kind of legacy of that, one of the key goals of the telescope that I'm about to tell you is to make sense of the dark universe, and in particular to focus on not the dark matter, but the dark energy, this material that we call it material, we call it dark energy, but whatever it is that is somehow causing the universe rather than to slow down. We would think that as the universe expands, we would think that everything would pull on everything else, and it would, and that the rate of expansion would slow down. But in fact, we find that it's speeding up. And so, among many other things, the Vera Rubin Observatory was envisaged as a way of answering and addressing some of these questions. And it's a very different base from most observatories, optical or otherwise. So let's meet it. It's now complete. It's been built. It was built over the last 10 or 12 years. It took a couple of years longer because of the C word that someone mentioned just recently. Slowed things up a little bit. The actual physical telescope itself is in Chile at La Serena, but the experiment itself is primarily an American experiment funded by the National Science Foundation, by the Department of Energy, and hopefully still, despite the various things that are going on in the United States at the moment, and also with significant input from private donors. It's a purpose-built 8-meter optical telescope, so not the very biggest optical telescope in the world, but certainly up there among large ones. But unlike your kind of standard Keck telescope or your VLT, that makes primarily what are known as pointed observations. In other words, you bid for time on the telescope, you point it at a particular object. The job of the Rubin Observatory of the Charles Simonyi telescope, one of the people who gave money to it, is that every 15 seconds it will take an image of the sky or the piece of sky that it's looking at, and it will keep that cadence up night after night, year after year, for a decade-long survey of the sun and sky. So this is the mock-up of the telescope. You can see, a little person standing there, and so it's always good when a plane comes together. So here's the telescope actually built and installed, and looking out into the southern sky. The heart of this telescope, it's short and fat, but the heart of this telescope is the world's most sophisticated digital camera. I haven't written down the number, but it's something like 3.26 gigapixels. But on top of just having a lot of pixels, it's got super low readout noise. It's got rafts of independent CCDs that are built into this thing, and you can get an idea of how big this is. Again, this is a ladder that a person can climb. This is a really possibly this described as the world's largest camera. And also, when it's installed in the telescope, you can see that it has the world's largest lens cap, which sits on the front of this camera. And here it is sitting in there ready to rock and roll. So when I was a kid, when I moved back to New Zealand at any rate, this thing was referred to as the LSST, which stood for the Large Synoptic Survey Telescope. But that was going to be a problem because we would have to explain to people what synoptic meant. So it was formed up into this telescope is going to carry out the legacy survey of space and time. And it turns out that's what's known as a backronym, where you create your acronym in order to fit something, a phrase that you already had. In this case, you sort of reverse engineer it into another more technical acronym to make it sound more pretty and beautiful. The astonishing thing about this is that usually with telescopes, you can have a small field of view, you can have a fast image, or you can have high quality. You're always having to choose 2 out of 3. Whereas with some very fancy engineering, the LSST is able to provide a very broad view of the sky. It's able to provide a huge amount of detail on the camera, so sub-arcsecond imaging, and it's able to provide a very fast image. So in 15 seconds, the camera shutter opens, and if I'm going to do it with this audience. Let's do it. Let's count to 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Gets a bit boring here, doesn't it? 12, 13, 14, 15. So in that time, this thing has seen approximately halfway to the edge of the universe. And so what would have been an all-night observation on the Palomar telescope when I was a kid is routinely finding objects at a redshift of 1 and beyond. And so because the image here is of a size that every 15 seconds in practice it has a filter wheel, so it takes multiple images and different set of filter bands. But it's going to image the whole southern sky every 4 days. Out to a redshift of 1 or better in the case of the brighter galaxies that it sees. And so what that does is it's not just imaging the sky, it's actually imaging a decent volume of the visible universe. So I think from memory, a redshift of 1, it's about a third of the way to the edge of the visible universe. And you can get a size of the scale of the camera from the full moon or from the size of the moon that's been projected there. So getting all of this thing to work is a huge amount of effort and challenge for the people involved. But its first commissioning images were produced just a couple of months ago. And so this one is, I understand it, it's a composite of 678 separate images from the telescope. It's what I always read actually as the Trifid Nebula, like the plant, but it's actually the Trifid Nebula, TRI-1F. ID nebula, and it means apparently Latin for 3 parts. So this is a Milky Way object. It's in the constellation Sagittarius, but this object here, or this video here of the Virgo cluster, is taken again from a series of images that were generated through the commissioning phase of the LSST, and so this is just panning around the Virgo cluster, and you can zoom in to each of these objects with just an astonishing amount of fidelity. So it's pre-recorded videos seem to be. But this whole video is actually about 800 megabytes for about a minute. It choked my I was downloading it at Airbnb, yeah, caused problems. And so you can see the size. And so the theory is, as I understand it, that for this particular video, that corresponds to the amount of data that we'll have on the whole sky after 10 years. So for that one, it's part of the commissioning. They hammered away at the same spot night after night. So what this does is it produces a river of data And in particular, it means that you can do time domain astronomy in a way that was previously unthinkable, and that you can look for things that change as a function of time. So at the moment, we have reliable observations of a few thousand supernovae that we can use to set the distances to objects, potentially out to a redshift of 1 or beyond, and use those to infer the expansion history of the universe. So not just the expansion is accelerating today, but also how fast and at what point that expansion turned on. Rubin won't have spectra, but it will be able to accurately measure redshifts from the different photometric filters that it uses, and it will see millions of supernovae during the course of its, so 1,000 times as many as we have at the moment, maybe 500,000. And so what will be done, rather than sort of pointing the telescope at particular things that are interesting, if you want to do science with this, you drop a different net. Whichever kind of science you want to do, you match your net to the kind of science that you're interested in, and then you effectively drop it in the river of data that is coming out of this telescope. So it's a very different way of doing optical astronomy in particular, and it's one that sort of lives in the world of big data and machine learning. On a nightly basis, they expect about 500,000 things that this will see, that this will see will have changed in some way, and potentially trigger alerts that will need to be followed up, firstly by automated brokers, and then eventually by people. So it's going to be an interesting challenge. So the question is okay, that's a cool thing. The Americans are doing it. So how do we get involved, and what do we do? And so it turns out that we can get involved with this, or countries, organizations can get involved with this by making what they call an in-kind contribution. And Nick knows, and Yvette has heard about is going to be involved with this, and our friends at Canterbury know, is that in New Zealand we have two things that are of interest and value to the Rubin collaboration, it turns out. The first of those is the MOA database. So the MOA images that Nick referred to, that archive of images stretches back to 2006 to maybe 2015. And so in those small patches of the sky that the MOA survey looks at, which is to say the center of the galaxy and the Magellanic Clouds, we can extend the reach of Rubin not to the same depth and resolution as Rubin, but we can extend its reach back to 2006. So we can provide a wee time machine for this experiment that will turn on in 2025 or early 2026. The other thing we can offer is that our friends at Canterbury and potentially elsewhere have telescopes. And so if something interesting is seen over the skies of Chile, 8 hours later, that same object will be over the night sky in the Southern Alps, and we'll be able to offer roboticized telescope time and Mount-Jonas to follow up. And so that is how we paid our way in to this to use of this $1 billion instrument and this multi-thousand person collaboration. So we can go fishing. We too can go fishing in this river of data. We can, in collaboration with international colleagues, we can participate in this work. I don't want to talk about money because money is kind of unclean and naughty, but I do want to talk about it because money is also hard to find. And so it means that maybe I shouldn't say this in front of our it's probably why this talk can't go online. But the total direct cost to New Zealand in terms of actual money we've had to spend to make this happen that we might not otherwise have spent is probably less than $1 million. But that means that we're being brought into a $1 billion project for the coming 10 years. Yes.
Just for comparison, $1 million is one Marsden project.
It's one Marsden project. It's 1/30th of what we spent to get into MethaneSat, which was the flagship of our space effort. And we could ask what return we've seen on that, for instance. I think that would be a thing that we could do. We might not get answers, but we could certainly do that thing if we wanted to. So the University of Auckland and Canterbury, and potentially we're hopefully talking to Victoria about the possibility of open seats in this. But what it amounts to is it's kind of a marketplace that allows us to turn a resource that we have that we can make available to Rubin that has value to Rubin And so we get a certain number of, there's a complicated spreadsheet, and we get 12 principal investigators, and each of those people can bring in 4 people underneath them. So about 50 people can be involved with this in the sense of having research access to the data, being able to publish papers, being able to join collaborations that are part of this. So for people in a small country, it also immediately plugs our people into a big, effective collaboration that has all kinds of networks for early career researchers, the kinds of support structure that we often struggle to provide here simply because we're kind of thin on the ground. And so that's a big slice of our astro research community that will participate in that. And when we look at the science that we're doing, that science ranges from looking at objects in the solar system. This telescope, it will see rocks that move in the solar system. I didn't show the slide, but one of the commissioning images shows literally thousands of asteroids that hadn't previously been catalogued. Every decent sized object in the solar system that's moving around, pretty much all of them will be found by Ribbon. One of the more fascinating categories of object they find is interstellar objects. So asteroid or cometary-like bodies that are moving freely through the Milky Way. It turns out large numbers of these objects are ejected from planetary systems as they form, or think they are, or my colleagues in Christchurch think they are. I don't know. I don't have an opinion on this. But so far, precisely 3 of these have been discovered. They have captured the world's attention, partly because of the work of a certain astronomer at Harvard, who read too much Arthur C. Clarke as a boy, and probably has not enough hobbies as a grown man. And I have to watch what I say because I have a paper with that gentleman. But claiming that this thing is not in fact a comet, but a space, sort of rendezvous from Rama style spacecraft. But these things are awesome, and one of the things that they do is that they want, so far we've seen 3 of them, and each of them are super cool, but they're 3 separate objects. What Ribbon will do is it will find 50 or 100 of these things, and it will allow us to do statistics on the population of them. Where do they come from? What kind of orbit are they in? And it will tell us things about the distribution of matter in the plane of the galaxy, in particular, not only the luminous matter that produces these things are made out of atoms, but also the dark matter, and these things will be surfing in the gravitational potential that's produced by the dark matter. It will tell us things about black holes in the Milky Way that might be chugging around the ground. Those microlensing, some set of words I want to use, extrasolar planets. It will tell us things about galaxies, and it will tell us things about cosmology, about the global structure and the evolution of the universe, all from the same data set. So rocks that could one day bump into the Earth through to objects halfway to the edge of the universe. It's kind of cool, and it's definitely fun. So here's an artist impression of the first interstellar object, just for fun. This is actually not a Rubin image. This one is actually, as you can see, if you read the thing, this is from the HST wide field camera. It's a 3 arc-second image, and you can see that at this point it started to produce a wee coma as it melts. But it turned out that one of the first science papers to be produced from Rubin was in fact a pre-discovery image of this, but certainly that was found in the engineering data. So they've been taking a series of images of the sky, not to do science, but to commission the telescope and to test that everything's working properly. And just by chance, they pointed it at the part of the sky where this thing was passing through. And so one of the first science papers to come out of Rubin was in fact observations that it had unintentionally taken of this comet, but also a proof of concept to show that it would have actually been able to see it and detect it. It stands out clearly in the images, and I picked out Michelle's name because Michelle Bannister at Canterbury plays a leading role inside of the community that's figuring out the properties of these things. But there's also actually, you can see Roberta Armelin, a colleague of ours in engineering at Auckland, who has an interest in both space situational awareness and asteroid trajectories has joined this collaboration as a result of our engagement with it. So what am I personally doing? I figured I should say something about that. I've been kind of nurturing this along since about 2011, really from before I arrived back in New Zealand. So those of you who know my trajectory, I moved back to New Zealand from the United States at the end of 2011. And in fact, over the Christmas break, I wrote my first official act as the head of department physics at Auckland was to write a letter of intent to say that we were super keen to get involved with this thing after checking carefully with the dean that I was allowed to do it. Don't want to get too far over your skis. I'm a member of the Dark Energy Science Collaboration inside at Ruben. So we're going to be thinking about there's a whole raft of things that we're going to do over the next 10 years. But in particular, my personal interest is that it turns out that there are theories, string theory being one of them, that says that there may be, particles is probably kind of a fuzzy word in this context, that may have a mass that's about 1,000,000 trillion times less than that of an electron. And these particles, they have quantum wavelengths that are measured in light years or hundreds of light years, or in some cases in thousands of light years, or sort of up towards, getting up towards kiloparsecs. And those things can kind of bridge dark energy and dark matter. And in particular, they're interesting because it seems like the dark energy isn't exactly the kind of dark energy we might have guessed. And dark matter sometimes seems like it might be a little more funky than we think it should be. And so it allows us to potentially stitch those two things together. And so Ruben will allow us to test those theories. So this is my halfway point. Anyone have any questions that they want to throw at me now? Yes.
So you said that the Variable Ripple Observatory is imaging the southern hemisphere skies.
Yeah, that's because it's in the southern
hemisphere. So my question to that was, what is the most northern declination that it gets to?
To be honest, I don't know. I have to go and check. But it's halfway down the southern hemisphere. It won't get too close to the horizon. But yeah, I would have to take notice on that and look at it. But certainly parts of the sky that are technically north of the celestial equator is not the south pole. The big problem actually is one of those big problems is going to be Starlink satellites. So as you look close to the horizon at dawn and close and not at midnight, you're going to see a lot of satellites that are illuminated by the sun. It's going to be a challenge.
Because what's the latitude? It'd be around about 38.
Something like that. Yeah. Yeah. I mean, I must admit I'm a theorist, so you're asking them. I'm at the hairy end of this.
This would be about plus 20, declination plus 20, maybe?
Yeah.
Everybody gets that.
Cool. So it's not going to be looking at Vega.
We should probably use these for.
All right. So we can try. So the question was is how far looks as a look, and my answer was to Google it. Any other questions that people want to ask? I've got the next half of my talk is Lisa. So that's all we're up to. And so it's a cool thing for New Zealand to be involved with. There's huge opportunities for our students, and it's a cunning way for us to take advantage of our heritage in some sense, to get involved in something that would be otherwise very hard to engage with. And we should say that every country that isn't America and Chile has got involved with it, has got involved in some similar way. Originally, the thought was that we would pay money, but it seems like the more likely, or that sort of failed for a variety of reasons. And so what they turned that into was saying that different countries have negotiated different contributions. So in fact, what we're doing is in fact the same as everybody else in terms of the process, but obviously not in terms of the particular deliverable. So the other thing, so it turns out Ruben is cool. It's getting underway now, and nominally the survey nominally has a 10-year lifespan. It's almost certain that something interesting will happen with the telescope once it's done. You don't build an instrument like that and then just forget about it. But it's going to keep us going until 2035 or 2036. And in many cases, you can imagine that the analysis will happen. Then you'll get more data, so you can improve your statistics. You can also improve your understanding of the instrument and its systematics. So there's going to be a gradual improvement of our ability to make sense of the large-scale properties of the universe. The other separate thing that we're doing is getting involved with the European Space Agency's LISA mission. And so LISA is not an optical telescope. It's not any kind of telescope. In fact, it is a gravitational wave detector. So it's not looking at electromagnetic waves at all. So it's astronomy, Jim, but not as you know. So question, this is a smart audience. So people have heard of gravitational waves, roughly speaking, ripples in space-time. And this, so how many people recognize this shot? This is one of the world's 3 or 4 currently working gravitational wave detectors. So this is half of the American LIGO instrument. This is the part that's at Hanford, not Stanford. So this is in the top left-hand corner of the United States. There's another one in the bottom right-hand corner of the United States in Louisiana. Well, not exactly all the way right, but sort of on the other corner of the country. I apologize to the Americans present in the room for doing such violence to their country's geometry and implying that it's a rectangle, but, roughly speaking, cows are spherical, then America is a rectangle. The reason you have 2 of them is because a car driving past this thing shakes it much more than the gravitational waves than you're trying to detect. So you want to be able to detect your gravitational waves in 2 instruments or more at once. The other thing you get is the gravitational waves travel at the speed of light, and in particular, the signals that are seen at LIGO are relatively short. And so the change in arrival time, and then when you add the Virgo detector in Europe and further detectors, you can also then deduce the position of the object that you're looking at on the sky. So how does this work? So what you're looking at primarily with this thing, with LIGO, is you're looking at very short, very intense bursts of gravitational waves. And so people often use this analogy that gravitational waves are like listening, and optical regular astronomy is like seeing. So it's like waiting for a hoot or for a siren to go off. Most of the time, you're just listening to the sort of background hiss, and the detector, if there's a signal to see in this thing, there'll be a sudden burst of energy, and that burst of energy will last typically for less than a second. And so what you should think about when you see this thing is actually this object here. So if we take 2 black holes and we put them very close to each other, they're in a very tight orbit. And everything that orbits around everything else emits gravitational waves. So the Earth orbiting the Sun is emitting gravitational radiation, but it would take quadrillions upon quadrillions upon quadrillions of years for that emission of gravitational radiation to make any appreciable difference to the Earth's orbit. On the other hand, 2 black holes, and the important thing is not so much that they're black holes, but black holes put a lot of material in a very small space. So that means that they can continue to orbit each other even as they get almost to the point of touching each other. Whereas if you use 2 stars, they would have, the distance, the separation of the black holes will be typically hundreds of kilometers. And so that, you need an object that fits inside of that radius to produce the best signal you can. And so this is one of the LIGO signals. This is a kind of visualization of it. And so every time the black hole makes an orbit, the gravitational waves carry away energy. And so just as a spacecraft, when it's starting to hit the top of the Earth's atmosphere, it loses energy. It pays for that energy by dropping a little bit lower, so it gets some bit of a speed up. Then it finds itself in a thicker part of the atmosphere. It loses energy more rapidly, and that last piece is a dive. And this is pretty much the same physics. The closer you get, the faster you move, the more quickly you do it, the more violently you're moving, the more you're accelerating, the more you're emitting gravitational radiation. And so those last few orbits happen very quickly. So you get a signal that is rising in frequency and rising in amplitude. And so it's what's technically known as a chirp. And again, there's going to be audience participation here. So we're going to do this, right, folks? We're going to go, ooh. So can we do this?
Yep.
And that's actually faster. Like the actual black hole merger, typically less than a second. So our chirp is actually a pretty slow one compared to some of these events. And so this is looking at stellar black holes. So black holes that have masses of 10 or 20 times, 30, maybe 50 times the mass of the sun. So the end point of the evolution of very large stars. So LISA, on the other hand, is something a little different. LISA, rather than having arms that are kilometers across, LISA has arms as a 3 spacecraft, and it has arms that are about 2.5 million kilometers across. And so what that does is that you kind of tune your instrument to much lower frequency gravitational waves when you do that. So the kinds of gravitational waves that LISA is sensitive to are actually, sort of a few tens of hertz through to a few hundred hertz. So very much in the kind of same band as, as kind of the audio that we listen to. This is picking up things from millihertz through to maybe a tenth of a hertz, so much, much lower frequencies. For the laser fans, the LISA detectors are actually Fabry-Perot interferometers, so they actually bounce the signal backwards and forwards on those mirrors. Their effective arm length is actually a couple of 100 kilometers, not 4 kilometers. They recycle the beam inside of them. LISA, on the other hand, only gets to use it once. So this is a geometry or a kind of concept that's been bandied around since, in fact, I think going back to the early 2000s. But it's only in the last year that the European Space Agency has decided that the technology is sufficiently mature that it is comfortable funding what will be a $1 billion mission to launch in 2035. So it's the European Space Agency's terminology for this is that they've adopted it, which makes it sound like they picked it up at the SPCA. So kind of he's sitting there, coming up to the front of the. But it means that it's now, there's money on the table. It's now that they're writing contracts with companies that will actually build it. It has a cunning orbit. I'll have to show this. So you can't keep it, triangles are rigid in space, but the 3 spacecraft follow an orbit that means that they can't wheel around each other. So, they take it in turns to be above and below the Earth's orbit. They're going to orbit about 10 or 20 degrees behind the Earth. And so it means that over the course of a year, obviously the orbit is, this is not completely to scale, but it means that over the course of the year, these things actually change the way that they're facing the targets that they look at. And so the signal that they see will be modulated with time. So these are much lower frequencies. And so what that means is that you're sensitive to much bigger black holes. So when you do the math of black hole mergers, the mass of the black hole in some sense is a free parameter. If you make the mass 10 times bigger, then you just change the time scale by a factor, by some multiplicative factor. But the actual shape of the signal is the same. And so the relative separations of these spacecraft, which are millions of kilometers apart, will be tracked to the nearest picometer, which is, I think, 10 to the minus 12 meters. And in order to do that, one of the cool things about this is that the spacecraft actually will not, at that level, the spacecraft will be buffeted by, sunlight shining on one side of it and not the other, by micrometeorites, all sorts of things. And so inside of the spacecraft, they have a test mass. And the spacecraft itself has tiny little rockets, tiny little thrusters that actually keep station on that test mass so that it's actually following a proper orbit around the sun, because you need that in order to back out the back that you're using to make sense of the gravitational wave. So this is scheduled for about 2035. Again, there's some debate as to whether NASA is going to change its focus, but the European Space Agency is committed to it and will see it through. But it's big science. It's $1 billion plus euros. So the kinds of black holes that you're going to see in LISA are very different from the kinds of black holes that you're going to detect in LIGO. In particular, the black holes that we expect LISA to be sensitive to are the supermassive black holes that we see at the centers of galaxies primarily. And so there's a supermassive black hole at the center of our galaxy. If you watch the stars very carefully, you see them orbiting around some invisible point in the sky that seems to weigh about 4 and a bit million times the mass of the sun, but otherwise, doesn't show up particularly in optical light. On the other hand, of course, to the radio astronomers, and it shows up nicely. It looks like a glazed donut. And you just get hungry looking at that. Also proves that whatever other failings it might have, the New York Times remains the paper of record for cosmology. Show this alongside the photo of the 1965 microwave background detection. Again, above, if you're above the fold in the New York Times, then you know that you've achieved something in cosmology. On the other hand, you've got migrants doing bad things, or people in America doing bad things to migrants. The Israel. So something about Israel. And I have to say, if you look at the 1965 CMB discovery, there's like a whole bunch of things going on that politics. There's a crooked New York cop. So you said on the page, there's something happening big in Honduras. But every so often, something cool happens and makes the New York Times. So we see pictures like this. This is a whole network of radio telescopes. You see pictures like this. The accretion disk, the light coming from the back side of it is kind of whipped around. It's bent around the black hole as it approaches us. So you see images like this potentially. And the one side of it is Doppler shifted as it comes towards us. The other side of it is redshifted as it moves away from us. These are real images. Also, you would recognize them from the movie Interstellar. So you get something like this, which is our black hole.
Sure.
Indeed. Planets are very big. Lisa, science. One of the things you can do is you can understand supermassive black hole mergers. So we think that big galaxies like the Milky Way grow by merging little galaxies together. The first galaxies to merge are relatively small, although we're rethinking some of that maybe in the light of what we're seeing at high redshift in the James Webb Space Telescope. And if all galaxies have a central black hole, then those black holes must either merge, or in the center of the Milky Way, we'd see a little globular cluster of black holes. And what we see is one big black hole. So we think that that the mergers of galaxies are followed by mergers of their central black holes. You also, inside of the Milky Way itself, you'll see white dwarf binaries, neutron star, combo, whatever combo of those things you want. And there's also the potential that there is to see gravitational waves that are sourced from physics in the very early universe. And anyone who doesn't have anything to do on Friday around lunchtime can come and see my talk, which will be a more technical talk about how the early universe might produce gravitational waves that are visible to Lisa. So when you do science with Lisa, you're really, the merger tree of black holes will recapitulate the merger tree of galaxies that, that produces the present state of the universe. So there is some sense that you're sensitive to the overall evolution of the universe. So we'll see supermassive black hole mergers out to the edge of the visible universe in Lisa. And from that, we can infer the expansion history of the universe, it turns out, by doing cunning things with the merger signals. We can also learn something about the physics or the ways in which galaxies are assembled. And as I said, there are ways in which the theories of the models of the early, the first trillionth of a second, where nonlinear processes in the early universe generate gravitational waves. Those aren't required. There's no guarantee that the universe will produce gravitational waves that Lisa can see, but there are many mechanisms that would do that, and so being able to show that they're not there even is a big step forward. So the New Zealand team has joined the Lisa Consortium a few years ago. It cost nothing to join, and I want to keep talking about money, but here I am doing it again. In this case, our time for 3 years was covered by a Marsden and Council Award, which is one of these big, kind of fancy Marsden Awards, I guess we call it that. So we got $3 million over 3 years, and it pays primarily for students and postdocs. So we've been able to make some headway on this, or make a contribution to this. So one of the kinds of things that we have done, my colleague Jan Eldridge at Auckland is an expert on binary stars. And so if you have a pair of binary white dwarfs, say once a pair of regular binary stars, and so the population of binary white dwarfs in the Milky Way will produce a signal that Lisa will see. The physics of merging supermassive black holes is something that I'm interested in. And there's also a whole separate problem. So with Lisa, with LIGO radar, you see one source at a time. It's very short. So whatever noise or whatever kind of parameters of your system, nothing changes in your system while it happens. Your noise is what the statistician's stationary. But Lisa is more like trying to listen to someone like eavesdrop on the people next to you at a cocktail party. And so there's hundreds of people talking. There are hundreds of sources that will be active in Lisa at a given instant. And what we want to do is to figure out, is to disentangle all of those conversations to the extent that we can. And it turns out that my colleague Renata Meyer in the statistics department at Auckland with Nelson Christensen, who now works in France, but used to, again, actually work in the 90s as a laser physicist at Auckland. They wrote some of the first papers on using fancy Bayesian statistical techniques to analyze the time series data that comes out of gravitational wave detectors. So New Zealand has, it turns out, this deep and rich heritage in what we call astrostatistics. And we're able to bring that expertise to the table and play a meaningful role in the work that Lisa is doing. So the key thing is that Lisa's signals will last for months, and maybe even the whole lifetime of the detector, LIGO for seconds, and Lisa will hear multiple things at a time. The parameters of the system will change. The thing's going to orbit the sun. It's also going to turn off periodically. When it goes behind the sun, we won't be able to talk to it. The spacecraft going to need to do housekeeping from time to time. So you won't have a continuous data stream that you can use, and that makes your analysis problem enormously harder. So my interest is in signals from the early universe, and also how it is that supermassive black holes and galaxies where we have funky dark matter might interact with each other, and potentially signatures of primordial black holes that interact with supermassive black holes. So I'm going to skip quickly over that, even though it's what I do and I love it. For the interest of staying in time. So this is astronomy. The key thing about gravitational waves is that, as we just heard from Nick, you can set up a medium 12, I should be metric, 30 centimeter telescope in your backyard, say, and you can absolutely do research grade astronomy if you know where to look and you've got a reasonably decent detector. The only way that you can do gravitational wave astronomy in a meaningful way is to spend hundreds of millions of dollars. There are no little gravitational wave detectors, or at least none that are able to see a meaningful signal. These things are primarily, they're almost physics experiments as much as they started, I guess, as a physics experiment and they've become astronomy experiments. So there's very much about, this is living at the overlap between deep gravitational physics, so Einstein's theory of relativity and things that we see in the sky. But we're hoping that it will help us reveal the kind of global history of the universe in ways that are synergistic with what we learn from optical telescopes. So we can do this. We've got lots of big teams, need lots of people. We've got great people, and so by getting our great people involved with this in some nimble footwork, again, we can do this world-class science on this relevant oily rig. So we're building a national collaboration. We have a bunch of new collaborations between. We've made this up for a grant report, but there's new people talking to each other at universities around the country that weren't previously doing that. And the very last thing I want to close on, if I've got a couple of minutes. Okay, is that a one or is that a thumbs up? I wasn't sure, maybe both. I was not talking about the why of this. Why should we do this? Why should we care? And for me, obviously, the answer is obvious because I think it's cool and I really enjoy it. But the other kind of deeper answer to this is that the United States, Europe, Japan, India, China, all of these people are investing heavily in fundamental science. They're not just doing it for fun. These are hard-nosed, serious people who know how to squeeze a dollar. So they must see something in it. And I think, I look at this image of Newton's apple tree, and I think the challenge for New Zealand, we've just had so I'm going to get political for a second, but today, I was approached for comment by the media about this big statement about, the future of New Zealand or the organisation of New Zealand University. And everyone wants the science system, universities or whatever, to produce things of value to the country. And so we're in favour of that. I think it's awesome. I think that's something that, we're supported from the public purse. We should absolutely give back to the public. The key thing is that I think what is missed is that too many people are asking what fruit that we can pick from the tree, and they're not asking, how's the tree doing? And the stuff that we're doing here is very much about it's about watering and fertilizing the tree, making sure that the trunk and the branches are healthy, so that the fruit that we want to pluck from this will grow in abundance on the tree of science. In other circumstances, New Zealand is super ambitious. We talk about tall poppy syndrome, but it's nonsense. We expect when we do things as a country, national, international, we expect to do well. Lisa Carrington is she's we send people like that to the Olympics in the expectation that we've maximised our chance of coming back with gold. We're not embarrassed about being excellent. We're not embarrassed about seeking to win. We're not embarrassed about seeking to stand out. But the problem in science is that we have not so much tall poppy syndrome, but sort of short poppy syndrome, and that we're planting seeds that will, that because there isn't a long-term consideration here that they won't, grow as healthily and abundant as this does. So, when we look at space, everything here is community organised. We have no real national plan. And so what we're unusual, I think unique globally, and that we have come together as a community and we have come up with a workable plan that will, the LISA will run, LISA conveniently starts as sort of the first decade of the LSST will wind up. So we've got a plan that will keep us going for maybe 15, maybe 20 years. Lisa will launch in 2035, maybe run for five, 6 years if we're lucky. So this is going to keep, this is a plan that's been built by the community. In other countries, the plan is sort of more negotiated between the community and funders, but we've just come up with a plan and then gone to the funders and asked for money. So there's no coordinated effort to maximise spillovers and benefits, and if there was, those spillovers and benefits would be larger, and it's a challenge to us as individuals to articulate that value to funding organisations and to the public. The last thing I want to say is that what we're doing here is the shop window of science. You can pick up books for children that have a little sign on it saying printed on non-toxic paper. And I was thinking, why would that be? And then I had children and realised that they're going to nibble. And so the idea of the Big Bang, which was kind of, front page of the New York Times, I would say exactly how many years before I was born, but not me. In the 1960s. It's stuff that we told toddlers about today. You can tell the phrase black hole was first used in the 1960s in this context. The idea of a black hole, in fact, famously dates back to about 1780. The Schwarzschild solution is early 1916. But the fact that we started discovering black holes in some number in space is the 1960s. And so these are ideas that have moved from the absolute cutting edge of science down to what it is that we tell children. We teach them to count, tell them about dinosaurs, and we should be making the most of this. And in New Zealand, we're in danger of leaving too much money on the table because we haven't. Well, there's no money on the table, but we're missing out on value and opportunity. And so, if anyone gets a chance to tell a story of people who have an opportunity to make a difference about this is a story that we should tell. So. On that note, I'm going to finish up. I'm very happy. 3 times now. So anyone who has any questions, I'm more than happy to take them. And thank you very much for listening.